Now, I was told there's an online question. Online questions have been asked, and one of them was asked for Paula Caselli, and so if she'll come up to answer it, if she's here. Oh, she's here. Thank you. Okay, so now we can have the question.
Yes. So the first question for Paula. The models of chemical catalysis consider that it is possible that there are nanoparticles in interstellar grains? Since the nanoparticles are more active against catalytic chemical reactions and have a large surface area, and also allow a better movement of the hydrogen atoms, spillover, for example. So that's that was phrased written with a question mark at the end. So I'm not sure what the exact question is. I'm just reading verbatim.
Yeah. Yes. Okay. So yeah, it's not clear completely actually the exact question what it is, but probably it's just trying to confirm this concept, because I understand. I mean, it's not so obvious, no. So, well, the thing that we can confirm is that definitely there are these nano particles in space. So, in molecular clouds, we have dust grains that goes from 10 angstrom in size up to probably a few micrometers inside in these dark clouds. So we know that they are there, and the chemistry that occurs on them, it's of course is a product of our models and laboratory work. So, and it fits well, because when then we implement the results from the laboratory work and also our models, when we apply these to the conditions of the molecular clouds that we see, we can reproduce, for example, the water ice that we measure, and we can reproduce the amount of H2 that we see in diffuse clouds. So we can then conclude that indeed the presence of these dust grains help in the production of at least some of the molecules that we see. So yeah, I understand it's not a direct, vision of the process, but we have a direct vision of the process in laboratories that in fact can show that these reactions happen very fast. And this is another point that you said about the fact that hydrogen atoms can move around very fast and even at low temperature and hydrogenate elements and molecules.
Thank you.
Yeah, Franz Geiger from Northwestern University. So I've got another question, follow-up question, I guess, to this. On the nanoparticles and the surface chemistry, maybe it links also with what Reggie was telling us, which is that these the particles are likely charged, and as they travel, for how long they travel, they're probably changing their charge from positive to negative. The screening length in the interstellar medium is 10 miles or something like that. So is there a possibility that there's actually electrostatic effects, surface charges at the particle surface in contact with just interstellar space, where a particle that might be positively charged interacts over long distances with one that's negatively charged? Could that lead to accretion? Has that been investigated?
Yes, actually you are touching something that we are currently working on, because indeed, yes, you're right, that there are electrostatic effects, and you expect, in fact, that in regions where you have a mixed population of, it's you, okay, sorry, I didn't see you, a mixed population of negatively and positively charged grains, and we know that this is the case, and in particular in these dark clouds and in the outer part of the dark clouds, we made some calculations, and we actually counted the charges, and there are these different populations, so we predicted that coagulation will be boosted up. And this, in fact, it's very interesting interesting because observationally there have been detection of scattered light in the micrometer wavelength, which cannot be understood unless you have big grains, so of actually several micrometer in size. So the answer to you is yes, and we are working on it.
Sorry, we'll get there.
That one, yeah, the one I've heard is similar. I've actually heard this in conjunction with, of all things, planet formation. How do you get planet formation started? How do you get little grains stick together and making big grains? In the old days, it was thought you had this gooey stuff on the outside, and the gooey stuff would act like glue and just hold everything together. But I don't think anyone's ever gotten that to work. And so the fallback, I think, has been, the process gets started by some charges of some sort, and it goes on from there. So.
So there were questions from the audience?
Yeah.
And then you wrap.
This Bruce Garrett, DOE, Basic Energy Sciences. So this is a more general question that for the panel that goes back to one that comment that Franz made earlier, which was 4 molecules in a year, right? And so data science, machine learning, we're hearing a lot about that. Those tools have really advanced tremendously, and they're pretty good at pattern recognition. It just seems like that's a tool that should be employed here. So my question is, how much is it, or is this not really an opportunity?
Well, in the laboratory, certainly that's a point of considerable emphasis, right? So we make these complicated chemical mixtures, these discharges, so we can find upwards, let's say, of 100 different molecules simultaneously, right? And so it's that's one of the things we're really trying to do is to the ultimate goal is real time, right? Real time analysis of a complex mixture. And so we're looking certainly into using machine learning algorithms because fundamentally rotational spectroscopy, the beauty of that approach is it's based on the molecular structure. And the molecular structure is, if you have a unique from a structure you have a unique set of rotational constants. And there's at most only 3, right, if it's a rigid molecule. So in that sense, it should be quite amenable to that approach. And so, but historically, I mean, we're I think at some level going through a transition because, like I said, certainly in astronomy, it used to be like the VLA was before it was upgraded was something like 7 or 8 megahertz bandwidth. Now it's 8,000 megahertz, right? The SMA, which is run by the Center for Astrophysics on Mauna Kea, their ultimate goal is to have 128 gigahertz of data in one observation. So every spectral lines, every observation done with radio telescopes will be by default a spectral line survey, right? And so we have a tremendous amount of data we need to be able to synthesize and assign, and we don't want to spend a lifetime doing it, right? And so certainly in the laboratory we're working very hard to try to do that.
Yeah, so I think I heard a talk earlier this week where machine learning applied to seismicity, right? But there it's, the subtitle of that talk was the information's in the noise. And so it's really, this thought came to me when Els was talking about, better resolution and stuff. But can you get something out of actually applying some of these data science techniques that would help you be
Okay, well, let him go first because he's, okay.
Susanna Whitticus-Weaver from Emory. So bridging off of what Mike said, there are a lot of efforts going on to be able to analyze broadband laboratory spectra and complex mixtures, and there are groups of us that are now starting to take those techniques and try to extend them to observational spectra so that we can use these methods. So it's coming, but we still have a long way to go with the laboratory work where we actually have benchmarks, and so the observational analysis is much more complicated, but it's coming. Yeah.
So Jake Yeston, again, from Science. I'm wondering that this was a really fascinating session from the standpoint of organic chemistry, but there was a sort of baseline assumption that there are these silica core particles there, which presumably would have formed through some kind of silicon chemistry. And I'm wondering if there are comparable efforts to understand how that works.
Either way. Yeah.
I'm sorry, you mean specifically how these silicon gradients form?
Yeah, in other words, just, the silicon chemistry analogous to the sort of carbon-centered chemistry that we heard so much about.
Yeah, so in sources of evolved carbon stars like IRC plus 16, there's a number of small silicon molecules that have been found. And so, again, with ALMA, you have incredible angular resolution and sensitivity and bandwidth. And so one of the issues is with ALMA, you can, compared to previous generation of interferometers, in IRC you have many molecules formed in this outer circumstellar dust region, and small, simple molecules right at the central star. And the resolution of previous facilities was not high enough. But with ALMA, we have a factor of 100 potentially higher angular resolution. So we can look spatially from the central star outward and look at the change in abundance of molecules and the formation of new ones. And we know from infrared measurements that the silicate feature is observed very close to the central star. And so, in fact, that's what we and other groups are looking at, is trying to identify many of these features that are only observed in the inner shell and disappear in the outer regions, and try to understand what they're due to. Presumably they're seeds of dust formation. And it's not at a high level in that we're only looking at small silicon molecules with half a dozen atoms or less. But potentially we can interferometrically look at the formation and destruction and correlate that with the infrared features.
Maybe I can add just 2 words about silicon, because silicon we don't see much at all actually in cold environments. So it's basically, yes, it's a refractory material, what we believe it is, and it mostly stays in the core of the grains, and maybe this means that it doesn't participate to a very active chemistry. We see a lot of this SiO, so oxygenated silicon, that we presume is actually coming from the refractory material, that in fact it is composed by silicon and oxygen and magnesium and other elements. And you see them next to stars, where actually they're in proximity of these winds that are driven by these young stars, because then you have shocks, and during these shocks you are peeling off the ice first, and then you also peeling off these silicates. And you can actually get quite a large abundances, so quite a lot of silicon goes back in the gas phase at that point, but then you're not seeing many more molecules. Say, you can see silicon carbide, SiC, SiO, but at the moment we are not seeing, the equivalent of this organic carbonaceous material. Yeah.
I was just going to add something for the point of view of the experimental physical chemist. Some of these things, they start with silane, SiH4 instead of CH4. And silane, in case you don't know, you open it up to the air and you get a fire. Okay, so there's a little bit of a discouragement from working with silane sometimes. If you have a leak with methane, like that Holy vacuum system I showed you, if you have a leak with methane, okay, all right. We worry a little bit, but with silane, you worry immediately about it. And so I don't know. We have a person at Goddard who does some of these things, and it's something you have to watch very carefully. They're very careful about safety in this and everything. So.
Yes, this is an online question.
Mm-hmm. Yes, we have another online question from Jose Aponte. And he's asking, so he's saying that water present in icy mantles is traditionally taken as non-reactive, inert species. Is this always the truth? And if not, what would the implication be for current astrochemical models?
I didn't get the first.
Correct me if I'm wrong. The question was thinking that the icy surfaces were pictured to be inert. But asking whether there were reactions going on?
Water present in icy mantles.
Right, and you wondered if the water is reactive.
Mm-hmm. Correct.
Well,
Well, I mean, water by itself indeed can sit there and being not very reactive, but as we have seen in space, even in the coldest and densest, most quiescent region in the interstellar medium, you still have these energetic particles that go through, and also some photons that are created by the energetic particles, these cosmic rays, and they can actually break bonds. And once you break the bond of the water, then you can start, doing a lot of interesting chemistry, because you liberate, for example, hydrogen. You have an OH molecule, and you can attach. You can think of many different type of. So you can actually have a rich chemistry out of water, just taking into account this extra energy that is in these clouds.
Also, you must have heard Reggie talking about radiolysis of water, ending up with OH and H and other things. So the answer is, I guess, it's not necessarily thermal. It's a more complicated environment. Yeah.
So I have a quick question. I want to aim it largely at Elle, since we haven't heard much from her. Other than more time with the instruments, what would you consider to be some technology gaps in the ability to identify some further complex molecules beyond what you've already found and what a lot of the industry has already found, as far as these complex polycyclic aromatic hydrocarbons? So technology and instrument gaps.
You mean for observing it from space or from the lab?
Being able to observe it in space from here.
Well, James Webb will really be the answer for pH research, because you get the spatial and the spectral high-resolution information over the full wavelength range. And that was lacking in the past, because with Spitzer we only had started at 5 microns, so we missed the short wavelength, and it was low resolution, and with ISO we didn't have the spatial information. So So for the infrared, the James Webb Space Telescope is really the next big thing. Now, some regions, even with James Webb, you could not still spatially resolve it. And so, so there the technology in order to, go on even on a spatial scale much further than what James Webb can do for sources which are barely resolved, would be, essential. I mean, in that sense, because then once you spatially resolve it, you can really go from, you can probe different populations and how it changed from one, instead of getting everything in one single pixel or spectrum.
Can I just add a couple of words here, or there is no time? Can I just answer?
Yes,
because I don't know, I think I understood that you also wanted to see what we can do from Earth. I mean, if from here, if we can help also this field. So maybe, I don't know, but, I'm just thinking. I was wondering if indeed, I mean, if we could set up, or maybe there are already, set up labs where you can actually expose all the pHs we know from Earth, and then expose to the try to recreate environmental conditions that are similar to what else was showing, like the PDRs and this dissociation, and try to see which is resisting there, which is thriving, and all these things, and then maybe this could be a good way to kind of help in the, but I'm sure it's much easy to say, but not very easy to do.
So I was going to just add that, of course, pH chemistry is combustion chemistry, right? I mean, fundamentally, it's so in that sense, there really is a lot of overlap with other communities. And so I think there's an opportunity there for the astronomers and combustion groups in particular. They have a lot of mutual interests in that sense. And, in some sense, it all relates also to this whole issue of reaction chemistry and reaction mechanisms, which chemists should be interested in more generally. So I think, in fact, there's lots of opportunity for advancement collectively.
So I'd like to ask a question very similar to yours, except talking about smaller molecules. So Catherine, what do you think are the largest molecules that could be seen in protoplanetary disks? And what technology might be used? Oh, okay, I'm taking it, right. Anyway, did you hear?
I can hear. Yeah, yes, I have my microphone turned up. So Eric's question was, what's the largest molecule we might expect to see in sort of planetary disk?
Yes, and how, if the new technology might exist to help.
So the state of the art at the moment, what we have at the moment is ALMA. That gives us sensitivity and spatial resolution. So some of the challenges that we have in seeing things that are bigger than methanol or methyl cyanide or formic acid is that the bigger the molecule, the more atoms, the more ways the molecule can distribute its energy into different energy levels, so the higher the partition function in the molecule. So what we know from studies that we've done so far is that the fractional abundance of these molecules in the gas phase is very low, of the order of 10 to the minus 11 relative to molecular hydrogen. And what we know about chemistry is that the larger the species, it tends to be a lower abundance. So that's one limit that we have, is that anything bigger is probably going to have a lower abundance in the gas phase. And then further to that, the lines that we expect, there's going to be more lines, and they're going to be the same amount of molecules going to be populated over those lines. So then that makes the line strength go down further. So we can try techniques such as using template spectra and looking at stacking multiple lines, but my feeling would be that it'd be difficult at the moment to get anything bigger than of the order of 6 or 7 atoms. We may be able to try to go and look for these long chain hydrocarbons, such as what Mike was talking about, because they're linear rotors and then they have less energy levels, even though they may be low abundance. So we might see something bigger, but I think we're probably hitting the ceiling of what we can do at the moment. Looking to the future, we can also look for these molecules at much longer wavelengths, at centimeter wavelengths, and that is traditionally how they've been found in the interstellar medium with things like the GBT, as Mike was saying. So we will have next generation centimeter interferometers coming on board, SKA, and also NGVLA looks like it'll be going ahead. So we need to really start looking at whether going to longer wavelengths might actually help us see bigger things. That would be my short, long answer to that question.
Okay. What about PAHs?
PAHs have been seen in this.
Yeah.
I see.
Yeah. So you can see them typically in disks around higher mass stars, around Herbig stars. They can't be attributed, I think, as Elsa said, to any particular PAH, but you can fit the spectral features using kind of the family of PAHs very often done in other similar UV irradiated environments. So we've already seen PAH emissions from protoplanetary disks, so we know PAHs are there.
So one thing that has always bothered me is we see these very large molecules, and the next largest ones we see have 12 atoms. So what about looking for things in between?
I think that's where the challenge is. So we have a little bit of a gap in terms of what we can really see with rotational spectroscopy at millimeter wavelengths, and then what we can see evidence for PAHs at near infrared wavelengths. But trying to get the size scale in between is a bit of a challenge in this. We just don't have enough material there to see, that's the problem. Most of the disk material is frozen, so we're reliant on that kind of low-level layers with a low abundance. We're trying to really detect things that are quite sticky once they're in the ice. We need them to be in the gas phase just about enough that we can see them. So we're kind of killed a little bit by the amount of the volume of material that we're trying to observe. Because as I said in my talk, they're just so tiny objects. That's part of the problem. We will get guidance from this large program that we're doing because we're really going in a quite high spatial resolution, and that can sometimes help if you have a very small emitting area. You can actually increase your signal to noise by capturing all of the emission from the molecule in smaller beams.
So if I may add to that, there have been searches going for for smaller cages. And so, because there are these magic numbers where you have C60 is a stable one, and then you have a few other more stable, smaller cages, but they have not been found. So far we only detected C60 and C70 in one source and nothing of the smaller ones. But people have been looking for them.
Well, we have people wanting to ask questions, so, but we've run out of time, or?
Yeah, we're a little past the time for ending, but maybe take one or two more questions, and then I think we're ready to move.
Okay. So we want another online question, I guess.
There are two online questions. So the first question is from Romulo Cruz about loop reactions. Is there any loop reaction discovered in astrochemistry today? And the loop reaction is when a reagent helps its own formation. And loop reactions are very important for the study of out-of-equilibrium process.
What's the word?
So is it loop?
Loop, yeah,
Okay.
like a loop reaction.
Cycle. Yeah, well,
cycle.
I can think of some, for example, but this is a very simple one, but I remember actually I studied with Eric many years ago, was the formation of H2 starting with actually sulfur, which sulfur is another one that is our friend in a sense that there are still lots of question marks but on the sulfur chemistry. But the loop here is, for example, you start with the sulfur atom that is landing on top of the dust grain, and then you have the hydrogenation, and you have HS. Then you have another hydrogenation, you have H2S, and then the next hydrogen that comes actually take one hydrogen and form a H2. And this can go on and make actually a pretty good way to form hydrogen on the surface of dust grains and get rid of, sulfur, to participate, say, in other type of chemistry. This is an example, but there definitely there are lots of loops, and some, for example, also for these ions, I'm pointing to him because he mentioned also, and Eric, the negatively charged, so the anion. You can have loops there with chemistry going with the recombination with the electrons and reformation, which are, these loops are actually very important because they can selectively give us a very simple chemical scheme, and then from that, once you have observations of some of these points, you can deduce the other. And in this case of negatively charged molecules, this is the electron fraction that basically we cannot really measure electrons in these clouds, dark clouds, so that is one way. I don't know if you want to add something.
Okay, one more question.
One more question. So this question is from Musso, G. Musso. And the question is about nitrogen oxide in interstellar space. So the question is, are there molecules of nitrogen oxide? Because nitrogen oxide chemistry is very rich and can generate many new products.
Yes. So there is NO. And we also know that NO likes to freeze out. And in fact, I remember a nice paper that say no NO in dense cold regions. And this is in fact, unlike CN, so nitrogen-bearing molecules that are either, for example, just containing nitrogen, like N2, etc., but also nitrogen-bearing molecules containing carbon, they like to stay in the gas phase. And this is something, as I mentioned, that is still a big question that we are trying to answer. But as soon as you add an oxygen, and NO is the simplest example, these molecules like to land on the grains. And what we believe is going on once they land on the grains, they will have, as this person actually mentioned, a rich chemistry. This is really something that it's very interesting for people who are working on surface chemistry in the lab to actually understand what are the products of NO. So stay tuned.
Okay, so let's thank the panel.
Yeah.